Hello,
Monaco,
Milks,
heat flow and heating and cooling curves.
coming at you live.
Very important skill set here.
Yes, we do need to be able to use these things to identify phase changes and changes in heat using said heat and cooling curves. Where are all the spots?
So this lecture is about all things heating and cooling curves. Next one will be about math.
Yes. So heating and cooling curve just plots the temperature over time while a substance is constantly heating. That's a lawyer statement, right? So I don't just like turn up the heat. It's going to be constant.
So kinetic energy is always changing when the temperature is changing, because temperature is a measure of average kinetic energy.
And it's on the y-axis.
So this is going to be the slants in our graphs.
There you go, bam. And I'm like, oh, check it, slants.
Boom, boom, boom.
That's what it
Anytime
means.
you see a slanted portion of a heating and cooling curve, the kinetic energy, aka temperature, is changing.
Nice. And then now there's potential energy changes. And this is when the temperature is constant. Because remember, I'm adding heat, but the temperature is not going up. But I'm adding heat. So where's all that energy going? It's going into changing the phase, which means the potential energy is changing. And this is specifically on the flats. So wherever it is on these horizontal lines, we call them the flats.
Yep. Slants and flats. So drawing, labeling, and interpreting a heating curve is simple. You start with temperature on the y, time on the x, and then you draw a slant, flat, slant, flat, slant for a heating curve. Make sure the slope is positive, headed up.
That's heating, going up.
And you've got three phases of matter. Solid is the first slant. Then it melts, tells you the melting point as well. Then we get to the liquid, which is the second slant. And then liquids vaporize, boil.
Same thing.
This is the phase change from liquid to gas. It tells you the boiling point as well. And then the final phase would be the gas.
Yeah. The only thing that's tricky there is a lot of times they never refer to it as the vaporization point.
No.
But they call it vaporization all the time, but it really is the boiling point. So those words are synonymous.
Synonyms.
Yes. So then we got to deal with energy on the same graph. So the kinetic energy is changing on the first slant because the temperature is changing. It's changing on the second slant. And it's also changing on the third slant. And where kinetic energy is not changing, but I am adding heat, the potential energy is changing on the flats. Cool.
Yep.
Cool. It's a lot to get in there, but you're gonna have to fill in some space and do down it.
So from a curve, finding melting and boiling point is, well, simply hit it, Milks.
Oh, sorry.
Push the button.
Push the button.
The melting point is the lower flat, and the boiling point is the higher flat. Simply, straightforward, that's what those values are.
Right. And where it's solid only is the lowest slant, where it's liquid only is the middle slant, and where it's gas is the highest slant.
Every single time.
And that applies to both heating and cooling curves.
Correct. Solid and liquid and gas, so mixed phases. So the lower flat is both solid and liquid because the solid is turning into a liquid. Both of them are present. The higher flat is where the liquid is turning into a gas, so both are technically present.
Correct. And then what intervals were kinetic energy changing? That's all the slants.
Yep. Potential energy changing is all the flats.
Facts. Let's do this whole thing over again in reverse.
Yep.
Drawing and labeling a cooling curve. So we're cooling, so all you gotta do now is, of course, temperature, time, but we're gonna start high and go low. So now we're gonna go slant, flat, slant, go.
And there you go, you take it away.
All right, well, top slant is going to be gas. First flat, condensation point. Now I'm going from gas to liquid, so it has a different phase change name. We call it condensation.
Yep.
Okay, and then again, the second flat will be liquids. And when I go from a liquid to a solid, freezing point. Okay. And then the last piece is solid only.
Yep.
You got energy.
Oh, yeah. So kinetic energy is changing in all of these slants.
Done.
And potential energy is changing in all of the flats because the principal type of motion and position of the atoms is changing during those times. You're going from all over the place to lined up and rolling and all that kind of stuff. So potential energy changes when the phase changes, kinetic energy changes when the temperature changes.
Every day of the week, which is nice. So find the condensation and freezing point.
Higher and lower flats.
It's getting redundant, I know.
Oh, yeah.
But it's important so we can label these things up.
Absolutely.
Gas is the highest slant, liquid is the middle, and solid is the lowest slant on a cooling curve.
The mixed phase points are where there you've got the flats. So the liquid and the gas are in the higher flat in this case, and the liquid and the solid are in the lower flat in this particular case.
Kinetic energy is always where there's slants.
Potential is always where there's flats.
Facts. Like it.
Now, exo and endothermic phase changes. Those graphs really were telling you all that you should have to know about exo and endothermic phase changes.
Yes.
But we're going to add a little more to it.
Just a little. So blue for cooling.
Mhm.
I go from vapor, which is a gas, to a liquid. That's definitely cooling.
Yep.
And when I go from liquid to a solid, we've done that before. I've taken liquid, put it in the freezer, and made ice cubes. I froze the water.
The interesting thing about cooling is that it's actually exothermic. And you might have thought that exothermic means releasing heat. And you're right. But here's the thing. When you release heat,
You get colder.
yeah, that's the part that people don't often realize.
Yeah.
They think exothermic means it gives off heat. Well, yeah, giving off heat is releasing heat, but we're talking about phase changes. And that heat that's being released when you take liquid water and freeze it is being released from the liquid into the fridge. The fridge soaks it up and kicks it out the back. I don't know if you've ever played around behind the fridge when it's operating. Behind the fridge is kind of warm and hot
Yes.
because it's taking all the heat from the food inside the fridge and sucking it out and kicking it out the back of the fridge.
Right.
So heat is exiting the fridge via the back of it. When you hold the door open too long, heat enters the fridge
Yes.
and everything gets messed up. So phasing down, exothermic, phasing
Yes.
down from gas to liquid to solid releases heat.
Yes. No, and I get it. He's right. It does seem to have a snafu there. The other one has none.
No.
The other one's obvious.
Yeah.
So when I go from ice to water, I heated it. And when I go from water to liquid, I heated it. But the thing is water feels hotter, but it's absorbing all that heat. It's endothermic. I have to add heat. It absorbs the heat. It changes phase.
Absolutely.
And that's about Good luck with flats and slants.
Flants. Good luck with the flants.
Yeah, with flats and slants. We do
Slants
need-
and flats.
I would very much advise you, when you have a blank graph, draw your slants first and then put in the boiling points and melting points and boiling points. Don't try to do the melting and boiling points first and then make your slants to it. Go ahead and do your slants and flats. Label it up from there.
You'll figure it out.
Yeah, you got it.
Clicky, clicky button, turny, turny off.